So, what we were talking about is the concept of refraction. And now, what we're going to do is once again look at our picture that has both reflection and refraction acting at a barrier. And before we started this, we mentioned last time that we have an angle here between the incident and normal ray, which is the angle of incidence, and that we know from the law of reflection that the angle between the reflected ray and the normal, which we typically call the angle of reflection with a lowercase r, these two are equal. We also mentioned that some of the light is going to get transmitted into this new medium, and we're going to call that the angle of refraction with a capital R. We also kind of were talking about the idea that while the angle of reflection is equal to the angle of incidence, the angle of refraction is actually going to be different. And what we're going to always see is that the angle is always going to be the smallest in the slower medium. So whatever we have, whatever we're moving through, it's going to be slower in that. And that's going to lead us to talking about how do we know how fast things are going? And that is using what we call the index of refraction. So the index of refraction is also known as the optical density of the medium. Think about this as if it were a hallway. If it's an empty hallway, it's like a vacuum, like you were running through the middle and you were able to just like run down the hallway at your absolute fastest speed. Compare that to, say, if a group of students from, say, primary school or EC are walking through the hallway, you probably aren't going to be able to go as fast, but still pretty fast, versus a situation where it's the change of class and there's multiple extra guests in the hallway. You're not moving super fast. So the more optically dense something is, the slower it's going to go. This index of refraction, practically used, for a lot of you, you may be taking organic chemistry in your future. And in the lab for that, frequently you'll use the index of refraction to check the purity of the clear, colorless liquid you create. Now, the index of refraction, n, is simply equal to the speed of light divided by the velocity of the wave. So, or the velocity of that light in that new medium. So, one of the things we can say here is that absolutely there is physically impossible for n to be less than 1. If n is less than 1, you broke physics. Don't break physics. And that means you can't use n less than 1 in future parts of a problem. You need to recognize that that is an issue and that you have to call yourself out for finding something that's physically impossible. Now, we did Snell's law, or we mentioned Snell's law previously, and this has to do with the angle of incidence and the angle of refraction. Again, everything relative to that normal. And we know that the index of refraction of the incident material times the sine of the angle of incidence is equal to the index of refraction of the refracted material times the sine of the angle of refraction. It's time for an actual example problem. And so we have light entering a piece of glass where n is 1.52 at an angle with the normal of 45 degrees, as we see in the diagram here. And you've got position A. First up, we need to mark where the angle of refraction would be. And so this would be our angle of refraction at A. And in order to find the angle of refraction at A, we need to think about some things. First of all, we change medium, or we cross a barrier. If we change medium or cross a barrier, we need to use Snell's law. Now, I know the angle of incidence, angle of refraction, all of that kind of stuff is, like we use those all the time. I'm going to label some stuff on the diagram to kind of help make it a little bit easier for me. And what I'm going to do is say that n is 1.52 when you're inside the glass, and the n for air, which would be on an equation sheet, would be, sorry, let me get that out there correctly. N for air is 1.0004. Okay. Now, what we would do and how I typically do it is instead of calling it incident or the starting material and the refracted material or the ending material, I tend to just use the name of the material. So I'm going to say that N for air times the sine of the angle in the air is going to equal N for the glass times the sine of the angle in the glass. And the theta R at A is going to be the theta, sorry, I'm not sure why I keep messing that up, of the glass. Okay, so doing a little bit of algebra and substitution all at once, we can say that theta RA, which was theta for the glass, is going to equal the inverse sine of taking N for air, 1.0004, times the sine of 45 degrees, and dividing that quantity by N for the glass, which is 1.52. Then we take the inverse sine of that whole dealio, and I want you to punch this through your calculator, and in doing so, you should get that it's 27.7 degrees. If you get it as 27.8, you typed in the value for the glass index of refraction incorrectly. Double check. Now, next up, we need to look for the angle of incidence at B. So in order to get there, you need to add in, here's our surface at B. So you need to add in, I already did this, the normal line at B. Okay, because remember, we always measure with the normal line. And in measuring with our normal line, that makes this our angle of incidence. Okay, so when we want to look at our angle of incidence here, we're going to need to think about what's going on. And in thinking about what's going on, we stay in the same medium. We stay in the glass the entire time. We don't cross a barrier. And if we don't cross a barrier, we can't use Snell's law. So what we have to use is geometry. So I'm going to do that right now. I'm going to take my glass is here. I have a normal line. I have my refracted ray that is becoming my incident ray. And I have my normal line here. And so this would be theta RA. And this one down here is theta I at B. Well, looking at all of this, we can see there is a right triangle. And with a right triangle, we know that the sum of the angles has to equal 180 degrees. And that with a right triangle, we know that the angle RA plus the angle IB have to equal 90. So that means theta IB would just be 90 minus the 27.73 on and on and on, making theta IB, 62.3 degrees. And so this is one of those big important things when you're dealing with moving through materials, that you have to actually take into account the thickness and where it's attaching and changing and all of that kind of stuff. Therefore, you have to actually pay attention to this. You can't just say that the angle of incidence from at the next surface is always going to be the complement of the refracted angle. It just depends on the geometry you're working with. So you have to pay attention to that. And finally, we're asked to find the theta r as it goes to cross B. Okay, so again, we're going to be crossing a barrier. Okay, and if we cross a barrier, we're going to need to use Snell's law. So I'm going to set this up again where I'm kind of like n for the glass times the sine of the angle of incidence in the glass is going to equal n for the air times the sine of theta in the air, which would be RB. So doing a little algebra and substitution all at once, we get theta RB is equal to the inverse sine of the quantity 1.52 times the sine of 62.2 yada yada yada, like it's like 27-ish or something like that. And we keep going. Make sure you're using the full numbers here. That's actually incredibly important. Divided by n for air, which is 1.0004. Now I want you to pause the video and actually run through this calculation right now. Cool, you're back. What you should have gotten is something like either undefined or error. Depending on your calculator, you'll get a different message. Make sure you check what it is. This just means that it bent so much that it actually stayed in the original glass and doesn't leave. That's why you see this drawing over here in the diagram.